Okay, in this video we're going to talk about Section 7D, and that deals with assessing risk. Okay, so here we're going to talk about risk and travel, and we're going to be looking at accident rates, birth rates, death rates, also which consist of vital statistics here. So here we go. Travel risk is often expressed in terms of an accident rate and death rate. Okay, so here's an illustration of a graph, and we want to ask the question, is driving getting safer? Okay, now here, this is what they did. They took the number of deaths in 1970, which was 52,100 deaths, and they compared that to the vehicle miles, which is in trillions. Okay, and that's, in this case, back in 1970, it was 1.1 times 10 to the 12 miles. Okay. Now keep in mind, trillion is 10 to the 12th power. So what they did was divided 52,100 by 1.1 times 10 to the 12th to get approximately 4.7 times 10 to the negative 8 deaths per mile. And then in 2011, which is over here, the number of deaths there was 32,000, and in this case here they used 2.9 times 10 to the 12 miles for 2011. Now in this case, if we do 32,000 divided by 2.9 times 10 to the 12th, we're going to get approximately 1.1 times 10 to the negative 8 death per mile. So if we compare 1970 to 2011, we can conclude that over the 4-decade period, the death rate per 100 million miles dropped from 4.7 to 1.1. That's a decrease of about 75%. In other words, driving became much safer over the period. Most researchers believe the improvements resulted from better automobile designs and from safety features such as shoulder belts and airbags. Okay. Alright, now let's take a look at example 1 on the next page. Here the table below shows the number of accidents, fatalities, hours flown, and miles flown for a country's airline with scheduled services in selected years. And here we're going to complete parts A and B below. In this case here, part A, we're going to compute the accident rate per million flight hours in 2006 and 2010. By this measure, has general aviation become safer? Okay, now let's take a look at the 2006 rate. That's going to be equal to, now we're dealing with accident rate per million. Well, the accidents in 2006 was 55. That's going to be divided by per million hours flight hours. Well, in 2006, that number of hours flown was 16.6. But keep in mind, it does say that it is in millions, so this will be 16.6. Now, for millions, that's going to be, in this case, 10 to the 6th power, because millions has 6 zeros in it. So it'll be 10 to the 6th power. So I'm going to have 16.6 times 10 to the 6 in the denominator. Now, what I would do, I would take that 55 and divide that by 16.6. And that will give me, I've already done this, 3.3 times that 10 to the 6 is in the denominator. When I pull that out of the denominator, it's going to be 10 to the negative 6. Okay? So, anytime you got an exponent in the denominator, you pull that out of the denominator, that exponent becomes negative. So we got 3.3 times 10 to the negative 6. Okay. Now, for 2010. The number of accidents is 25, divided by the hours flown in millions, that's 17.2. But that's going to be multiplied by 10 to the 6th power. Now, if I divide 25 by 17.2, I'm going to get approximately 1.5 times that 10 to the 6 in the denominator will become 10 to the negative 6 when I take it out. Okay, so now to answer part A, has general aviation become safer? By comparing these two, this amount is lower. This amount in 2010 is lower than the one in 2006. So general aviation has become safer because the accident rate in 2006, which is in this case, and I'm just going to write this as 3.3, because the answer, the way that it's written, is going to be 3.3 accidents per million flight hours. It's higher than the accident rate in 2010, which is going to be 1.5 accidents per million flight hours. Okay, that's the answer to part A. Now in part B, we're going to compute the accident rate per billion miles flown in 2006 and 2010. By this measure, has travel on the country's airlines become safer? So for the 2006 rate, in this case here we're dealing with the accident rate again, which is 55, divided by the miles flown in billions. That's 7.2. Now keep in mind, billions is going to be 10 to the 9th. Millions is 10 to the 6th, and billions is 10 to the 9th. So it'll be 55 divided by the 7.2 times 10 to the 9th. Now if I take 55, divide that by 7.2, I'm going to get 7.6. And that'll be multiplied by 10 to the negative 9. Okay? So I'm pulling 10 to the 9th out of the denominator, and that will become a negative exponent. Okay, now for the 2010 rate. I'm going to have to do this at the bottom. Here, the 2010 rate, the number of accidents is 25, divided by the miles flown in 2010, that's 7.6 times 10 to the 9th. Now if I do 25 divided by 17.2, I'm going to end up with approximately 3.3, and that's going to be multiplied by 10 to the negative 9. Now all I have to do here is compare these numbers that are in front. Okay? Has the travel in the country's airlines become safer? It has, because this number in 2010 is lower than the number in 2006. So general aviation has become safer because the accident rate in 2006 at 7.6 accidents per billion miles is higher than the accident rate in 2010, which is 3.3 accidents per billion miles. Alright, next we're going to talk about vital statistics. Data concerning births and deaths of citizens called vital statistics are important to understand risk-benefit trade-offs. Demographers use birth and death rates to predict future population trends. One important set of vital statistics covers causes of death. So here we looked on example 2. You'll see the table shows the leading causes of death in a certain country in a recent year. The population of the country was 312 million. What was the empirical probability of death by accidents during a single year? How much greater is the risk of death by accidents than death by suicide? Okay? Let's start off with the accidents here. The number of accidents we have here is 122,700 as given in the table. Now we're told the population of the country was 312 million. I'm going to write 312 million like this. 312 with 6 zeros behind it. Okay. So now to find the empirical probability of that, we take the number of accidents, which is 122,700, and divide that by 312 million. And I think I can do this on this calculator here. And usually depends upon what type of calculator you have, the 83 or the 84. Here I got the 84. So if I do 122,700 divided by 312 with 6 zeros behind it, it's going to give me that as a number in scientific notation. But in this case, that tells me that e to the negative 4 tells me I need to move the decimal point here 4 places to the left. So I know I can move it over 1 place, but I need to move it over 3 more places. So I'm going to need 3 zeros. And I'm going to give that answer to 5 decimal places. Alright, next we'll look at suicide. Which was, in this case, 38,400. And we already got the population of 312 million, so that means the empirical probability will be that 38,400 divided by 312 million. Yeah, and this also gives me a answer in scientific notation. Here I need to move the decimal point 4 places to the left because of the e to the negative 4. So here I only got room for 1, so I know I'm going to need 3 zeros in front of that 1. So it'll be 0.00001, 2. Okay. Now I need to find out what that empirical probability was, because I want to find out how much greater is, let's see, the empirical probability of death by accidents in a single year. That's the 0.000039. Okay, now we want to find out how much greater is the risk of death by accidents than death by suicide. I'm just going to divide these two together. So here, the risk between the two will be 0.00039 divided by 0.00012. And here they want this rounded to one decimal place, so this is going to be like 3.3. So to answer that question, the risk of death by accidents is 3.3 times greater than the risk by death of suicide. Okay. Alright, here's another example that deals with the vital statistics. Here we go. The table shows the leading causes of death in a certain country in a recent year. The population of the country was 313 million. If you live in a typical city of 500,000, how many people would you expect to die of kidney disease each year? Okay, let's look at how many people died of kidney disease. In this case, it was 45,300. And the population of this certain country that they're dealing with was 313 million. And that's how I write 313 million. 313 with 6 zeros behind it. Okay, now let's find out what the empirical probability is going to be. Okay, we take the number of deaths from kidney disease, that's 45,300, divide that by the 313 million. That's the population of the entire country, of that certain country. So when I do 45,300 divided by 313 million, I kind of figure I was going to get a number in scientific notation with this calculator. In this case, I need to move the decimal point 4 places to the left, so I only got room for 1, but I need to put 3 zeros in front. I'm going to carry this out to like 14.47, 0.000147. That'll be as far as I'll go with that. That's the empirical probability. Now, it does say here, if you live in a typical city of 500,000, how many people would you expect to die of kidney disease each year? So we're going to say the expected death from kidney disease. We're going to take that 0.000147 and multiply that by 500,000. In fact, if you want to, you can use that whole thing right there and just say times 500,000. And if I was to round to the nearest person, we're going to have to round up. So in this case, it will be 73. So about 73 people would be expected to die of kidney disease each year. 73 people if we lived in a typical city of 500,000. Okay. Next we'll look at life expectancy. Life expectancy is the number of additional years a person of a given age today can expect to live on average. Okay? And as you can see here, and I know this is in black and white, but here, as we, in the 1900s, in the early 1900s, 1910, up to 1920, men lived longer than women. But ever since 1920, women have a longer life expectancy than men. Okay. Alright, now let's look at this example about life expectancy. In a certain country, the life expectancy for women in 1900 was 48 years, and in 2000 it was 79 years. Assuming that life expectancy between 2010 and 2100 increases by the same percentage as it did between 1900 and 2000, what will the life expectancy be for women in 2100? Okay, now the way we're going to do that, we need to take what the life expectancy was in 2000, subtract from it the life expectancy, hard to talk, in 1900, divide that by the life expectancy in 1900. And that's going to be multiplied by 100%. Okay? You have to think of this. The new minus the old divided by the old and then multiplied by 100. So the life expectancy in 2000 was 79 years minus the life expectancy in 1900 for women was 48. That's going to be divided by the life expectancy for women in 1900, that was 48, and then multiply that by 100%. So in this case, I'm going to put the 79 minus 48 in parentheses, and then divide that by 48. That will be the decimal, but here I need to multiply by 100% because they want that as a percent. So if I was to round that off to, let's say, the nearest whole number, that would be 64.6. I mean, to one decimal place, it would be 64.6%. Okay? So the change in the life expectancy for women from 1900 to 2000 was 64.6%. Now the other part of the question is this. Assuming that the life expectancy between 2000 and 2100 will increase by the same percentage as it did between 1900 and 2000. The life expectancy for women in 2100 will be how many years? Well, if the life expectancy in 2000 was 79 years, let's take the 79 years, multiply that by 64.6%. Now, of course, to change a percent to a decimal, we drop the percent sign and divide by 100. This would give you 0.646. So 79 times 0.646 will give you 51.034. Now I'm going to round that off to the nearest whole number. That's going to be approximately 51 years. That represents the increase in a woman's life expectancy. So to find the life expectancy for women in 2100, we take that 79, which was the life expectancy in 2000, add that to the 51 years. And this will give you 130 years. So the life expectancy for women in 2100 would be 130 years. Okay. Right, here's another example. This is example 5. Country A reported 40,148 votes for a year, assume 365 days in a year, with a population of about 2.8 million people. Country B reported 12,188 votes, with a population of about 1.2 million people. So here we're going to answer parts A through D. In part A, how many people were born each day of the year in country A? So here we're going to find the number of births a day. And this is going to be in country A. That's going to be equal to the number of births in country A, which is 40,148, divided by the actually 365, because we're looking for the number of births per day. So 40,148 divided by 365, and I'm going to round that out to the nearest whole number. We get 109.9945, but to the nearest whole number, it will be 110. So the number of births a day in that country will be 110. And then part B, how many people were born each day of the year in country B? So here we do the same thing as we did in part A. But here we're going to find the number of births a day. And this is country B. Country B has reported 12,188 births. So that's 12,188 divided by 365 days in a year. So here, 12,188 divided by 365, which would give me approximately, to the nearest whole number, 33. So there were 33 people born each day of the year in country B. Now in part C, we're going to find the birth rate in country A per 1,000 people. That's very important. Okay, so now let me move the paper up. So now the birth rate in country A, the way we find that, you have to take the number of births that were in country A, which was 40,148, divide that by the population in country A. So here the population there was 2.8 million people. Okay, let's see, 2.8, and if it's in million, we have to multiply that by 1 million. That would give me 2,800,000. So 40,148 divided by 2,800,000 . Okay, that's that amount. But of course we need to multiply because they give us this per 1,000. So I'm going to take that 0.014338 and multiply that by 1,000. And to the nearest tenth or to the nearest whole number, it's going to be 14.3. So in country A, the birth rate is 14.3 births per 1,000 people. Okay, so per 1,000 people, that's why I had to multiply by 1,000. Okay, now part D. What was the birth rate in country B in births per 1,000 people? So we're going to do the same thing here. The birth rate for country B, well, how many births were there in country B? There were 12,188. That's going to be divided by, country B had a population of 1.2 million people. So if I take, let's say 1.2, and million is going to be 6, a 1 with 6 zeros behind it. Multiply that, you're going to get 1,200,000. So take 12,188, divide that by 1,200,000. We're going to say that's going to be 0.010567. But of course we need to multiply by 1,000 because it says births per 1,000 people. So multiply that decimal by 1,000. And we're going to round that up to one decimal place. This will be approximately 10.2. So the birth rate in country B was 10.2 births per 1,000 people. Okay. So that's how we do that particular example here. Okay, last example in this video. In 2015, the highest and lowest death rates in a country were in regions A and B, respectively. Region A reported 22,335 deaths with a population of 1.8 million. Region B reported 11,121 deaths with a population of 1.3 million. So here we're going to compute the death rates in region A and B in deaths per 100,000 people. How many people die each day in region A, and how many people die each day in region B. So in part A, the death rate in region A was how many deaths per 1,000 people. In this case here, the death rate, and I'll say in region A, we take the number of deaths in region A, which was 22,335, divided by the population in region A, 1.8 million. 1.8 million. So we'll do 1.8, multiply that by 1 million to get 1,800,000. Okay. Now, it's going to be per 100,000 people, so I'm going to go ahead and say times 100,000. So in this case here, when I do 22,335 divided by 1,800,000, and then times 100,000. Now, if I round that off to the nearest whole number, that will be 1,241. So the death rate in region A is 1,241. And now for the death rate in region B, we do the same thing. This is in region B. The death number of deaths in region B was 11,121. We're going to divide that by the 1.3 million, which was the population in region B. So if I do 1.3 times 1 million, I'm going to have 1,300,000. Then I'm going to multiply that by 100,000 because I want that as deaths per 100,000 people, as indicated in the problem. So if I do 11,121 divided by 1,300,000 times 100,000. To the nearest whole number, that will be 855. So the death rate in region B was 855 deaths per 100,000 people. Okay, so all of that was part A. Part B is finding how many people died each day in region A. Okay, now if this was reported on an annual basis, these are the number of deaths in 1 year. Now keep in mind, each day there are 365 days in a year. So in part B, the death per day in region A that's going to be the number of deaths in region A. That was 22,335. We divide that by 365 days in a single year. So 22,335 divided by 365 would give us, and they say to the nearest whole number in that example, so it's going to be 61. So each day 61 people die in region A. Okay, and then part C, how many people die in each day in region B. So again, we do the same thing as we did in part B. The death per day in region B, that's going to be the number of deaths in region B. That was 11,121. We divide that by 365 days in a single year. So 11,121 divided by 365. To the nearest whole number, that's going to be 30. So in this case, each day, 30 people die in region B. Okay, so that will complete this video on assessing risk.